So let's talk about this a little more generally now. This process is called identification, and that is the process of linking a causal estimand, the causal, for example, the causal ATE, to an observable estimand like that naive ATE, and saying, actually, these are the same in this special case. So that's what we're going to do here. And the general structure of identification proofs are always that. So we start by saying, under some assumptions, like treatment is random. Okay, that's an assumption. Then do some math. Math usually has to do with deciding on conditioning on some things and pulling some things out and exploiting conditional expectation and independence. And then the punchline is that you have the causal estimand and it's equal to some other thing. And this other thing is something that has no potential outcomes in it. So this is the thing that I actually want. It has potential outcomes in it. That's a problem because I never get to see these. But I can define it equivalently in terms of stuff that I do get to see. So I can estimate that. And this is what I call the observable estimand. And sometimes you'll see like people say statistical estimand, whereas this is the causal estimand or causal target parameter, statistical target parameter. Those words all kind of mean the same thing. There's two worlds, causal world, observable world. And those are the terms that I'm going to use. And as I said, the causal estimand is something that you cannot estimate from the data we observe unless you make certain assumptions, in which case it's equal to this observable estimand, which you can estimate from the data we observe. And this is the key. This is the main thing from this lecture. So another picture to kind of illustrate it, we have this causal data generating process, right, in which some confounder impacts what treatment people get. It also impacts the potential outcomes that somebody has. And you have a causal estimand that's defined relative to this causal data generating process. Like we want the expected value of this random variable. And that takes some value, right? Well, we don't ever get to see data drawn from this causal data generating process. Our data are drawn from this observable data generating process, which is related to the causal DGP. And how is it related? Well, we say that the observed outcome is the potential outcome corresponding to whatever treatment that person got. And then we don't get to see those potential outcomes anymore. So this is like that table that we were looking at before, where we had y0, y1, and then y is kind of just this combination of y0 and y1 depending on what a is. And here I'm just representing those two setups with these DAGs. And our question is, well, how the heck can we get from the observable data generating process to the value of the causal estimand? And in particular, we don't actually even get to know the observable data generating process. What we get to know is data that are drawn from that observable data generating process. So it's really a two-step thing, right? First, we have to use these data to estimate something about this DGP, and then say, does that thing that we estimated actually tell us anything about the thing that we really care about over here? So that is exactly what we are doing with identification. We're saying, well, we can take care of this first part of it, which is at least defining that under some assumptions, this causal estimand is equivalent to this thing that we can define just in reference to the observable data generating process. So I don't have to see y0 and y1. I can just see y and a and x, and then I can tell you something about this thing, which is kind of magical. And more generally, we can write it like this. So if we write the causal data generating process as p star, and we write it transforms according to this observation model, like for example, y equals ya, more generally, whatever that is. There's maybe some data that we're missing, some data that we don't get to see. That transforms this data generating process into P, which is the observable data generating process. And then we have two estimands. So there's psi star, which is the causal estimand. This is a thing that's defined. You can think of this as a function that takes the causal data generating process and gives you a number. And then you have some other estimand, which I call the observable estimand, which takes as an input the observable data generating process and gives you a number out. And it just so happens that these things give you the same answer under these assumptions that you've made, like treatment is randomized. And why is this good? Because it solves the problem. So we actually have, what we have is not this observable data generating process. What we have really is data, right? This is us here. We only get to see the data. But we're going to work backwards. Okay, so from the data, we have an estimator. That estimator is estimating the observable estimand And then we know that the observable estimand is equal to the causal estimand under our assumptions. So it's actually a two-step process. I mean, this is not anything you actually have to do. You just have to understand the assumptions, right? You just have to know, if I assume this, then these two things are the same. This part is something you actually have to do, right? You have to use the data to estimate it. But this is just something you have to like imagine or understand, right? And this is causal inference. So if you hear the words causal inference, it is this. And really, there's no such thing as causal inference. There's only two things. There's the causal part and there's the inference part. And they're really separate. So inference is everything that we've been talking about in the statistics portion of the course, or, you know, estimators and estimands. So basically, you can, once you get to the once you've done the identification part and you've said, okay, really I'm interested in this causal estimand, but I identify it with this observable estimand. After you've done that, then you can just forget about, once you have gotten the identification part done, and you've done made whatever assumption that you need to make in order to identify your causal estimand with the observable estimand, you can just forget about all this, okay? Who cares? Now you just have an estimand, you have a data entry process, you have data, you want to figure out, how do I estimate it? That's just statistics. It's just pure statistics. You don't have to think about what this thing means because you've already solved that problem with the identification. And it's not related to the estimator. So when you're using an estimator to identify a causal quantity, or to estimate a causal quantity, it's not like you need to design the estimator in a different way. It's just that usually whatever thing you're trying to estimate has to change so that you know that it's actually representative of this causal estimate. So for example, here we'll see it at the end of this lecture, where, you know, the thing that you're trying to estimate is not the naive ATE per se. It just so happens under certain assumptions that the naive ATE identifies the causal estimand. But in other cases, it might not, and you might need to go after something else. But once you have that thing set, this whole part is just a kind of algorithmic, take a thing, try to estimate it kind of process. So there's nothing special about that. It's what we've already seen. So now this begs the question, right? What assumptions do we need? So I showed that if A is randomized, if the exposure is randomized, then the causal estimand is identified by this quantity, which is like the naive ATE. But are there different assumptions that might work as well, where I can get something else over here? Is there something weaker? And so now we're going to talk about what we mean by assumptions, and wrap our heads around that a little bit better.